For decades, product engineering followed one philosophy: build a functional internal skeleton to do the heavy lifting and cover it with a sleek exterior skin. We classified these outer coverings as secondary materials. Trim, padding, and fairings were often chosen at the end of the design cycle because they carried no physical load. But across several unrelated industries, that separation of skeleton and skin is beginning to disappear. This shift is driven by a changing load path. Physical stress is migrating outward from the internal skeleton into the outermost covering. Components that were once purely aesthetic are now tasked with keeping the machine and the people inside alive. Pilatus Aircraft recently opened a new center of advanced composite competence in Switzerland. The facility is designed to move composites out of their traditional role as secondary fairings and panels. In aerospace, the certification threshold is literal. If a secondary structure fails, it falls off, but the plane flies. If a primary structure fails, the aircraft stops flying. Pilatus is moving composites across that threshold, shifting them from cosmetic shells into primary, load-bearing control surfaces. We see the same transition in spaceflight. Canova recently tested hybrid composite landing legs designed for the famous reusable rocket. This chart illustrates the impact. These filament-wound legs carry the full load of the rocket while cutting mass by 25 to 30% compared to an all-metal design. In these high-stakes environments, the outer skin has moved past its role as a cosmetic finish to become a critical part of the aircraft structure. These principles are also surfacing in consumer products. Jaisu Yoon's Re-Flat Pack sofa shows how this works even without the pressure of aerospace regulations. The design eliminates foam entirely. While foam provides comfort, it is also the first component to fail under repeated compression. Instead, the sofa uses woven nitinol wire. This single structure must simultaneously carry the weight of the user and provide the necessary flex. A similar logic appears in a recent action camera design study, where the traditional protective body is replaced by a single thick sapphire disc. In this camera, the lens optic acts as the primary structure. It takes the impact at its thickest outer edge, allowing the electronics to be reduced to a sealed ring at the rim. By pushing the structural burden into the skin, designers can specify materials purely for their durability while hiding the appearance layer behind a wear-resistant surface. From heavy-lift rockets to living room furniture, the material you see and the material that handles the physical load are becoming the same thing. This shift changes the timeline of product design. We have to reconsider when decisions about a product's surface are actually made. Choices regarding color, material, and finish, or CMF, can no longer wait until the end of the process. When the surface is structural, CMF choices become engineering decisions. As this timeline shows, these details must enter the program much earlier than they currently do. Decisions about appearance and wear layers must be locked in at the earliest conceptual stage, inverting the traditional workflow. Because these aesthetic choices are now load-bearing, they require rigorous testing and visualization before physical tooling begins. This creates a need for tools like Depix Design Intelligence, which can model these complex material integrations while the product is still a digital concept. Precise visualization is now a structural necessity. Design decisions are inexpensive as a sketch, but they become permanent once the material is tooled.